Today we're going to talk about dimensional analysis. Now, contrary to popular belief, generally physics is not concerned with the numerical values of quantities. It's more interested in the relationships between physical quantities. And that's what dimensional analysis is all about. And so one way of deducing the relationship between quantities is using this concept of dimensional analysis. The main idea of dimensional analysis that we need to talk about is the idea of physical dimensions. In physical dimensions, every quantity has a dimension. We denote the dimension in square brackets. This is most easily seen in some examples. For instance, square brackets with an L denotes length, and the common SI unit for that is meters. An M in square brackets denotes mass, with its SI units of kilograms, and a T in square brackets we use to denote time, and the SI unit is seconds. It's worth talking about some other quantities as well, because they show up very often. For instance, speed has units of length over time, or again in SI units, meters per second. Acceleration, which has units of length per time squared, or in SI units, meters per second squared. Force, which has units of mass times length over time squared, or kilograms meters per second squared, otherwise known as a Newton. Energy, which has units of mass times length squared over time squared, or kilogram meter squared second squared in SI units, otherwise known as a joule. And power, which has units of mass times length squared over time cubed. In SI units, it's kilogram meter squared per second cubed, or which is a watt, and a watt is a joule per second. A simple example of physical dimensions is the volume of a sphere. So the volume of a sphere of radius r is 4/3 pi r cubed. In physical dimensions, this is just length cubed. Notice that the 4/3 pi don't have any units, and so they don't contribute to the physical dimension. Let's consider another example where you actually might want to use the idea of physical dimension. Namely, consider this formula for the speed of an object. The speed as a function of time is the initial speed minus 1/2 times the acceleration due to gravity times t squared. And the question we're interested in is this formula correct? Well, we can use units to analyze this, so let's rewrite the equation and write each term in terms of its physical dimension. Speed is units of length over time, same for initial speed. Acceleration has units of length per time squared, and time has, of course, units of time squared. We see that the units of time squared cancels out, and so this last term has units of length. And so we see this last term has units of length. And this does not have the right units because it doesn't match the units of speed, which is length over time. And so we can conclude that this equation cannot be correct. Let's consider another example where a particle experiences non-uniform acceleration, where the acceleration as a function of time is equal to some constant k over time squared. And we want to know what are the units of k. Again, we can do this using dimensional analysis, rewriting each term in terms of their physical dimensions. Acceleration has units of length over time squared. The right-hand side has units of k over units of time squared. And so clearly, k has units of length. Finally, let's consider what happens in the case where we have differentials and integrals. So for instance, this expression, which tells us the final velocity of an object subject to an acceleration which depends on time, the final velocity is the initial velocity plus the integral of acceleration over time. Let's examine the physical dimensions of each term in turn. As before, velocity and speed have units of length per time. We don't really know what to do with this integral sign yet, so we'll just leave that blank for now. The acceleration has units of length per time squared, and then we also have to do something with the units of dt. So let's talk about what to do with this dt. So dt is an infinitesimal amount of time, and being an infinitesimal amount of time, that means it's just a small amount of time, and so it has also the dimensions of time. And so we put dimensions of time for dt, and then we see that the time dimensions partially cancel, leaving us with length per time for a of t times dt, and that's the right units for speed or velocity. And so we see that now the integral sign must have no dimensions. It doesn't have any physical dimensions. It is not really a quantity after all. It's more of an operation. So that concludes the introduction of dimensional analysis. Next we'll consider why you would ever want to use dimensional analysis.